Okay, well, 10. Temporarily, the iPad is working. So what we want to do today is start to introduce to the NMR. And I think what we'll do is we have lecture till around 2, take a 5-minute break, and then work on the first problem set. And then we'll talk about the problem set. Not to leave it really powerful. So let's start and imagine a conducting experiment. Up there. Hopefully it'll go away. Where we have an IF spin system, and we're going to make the first pulse selective on the I spin, and then the second pulse will be non-selective on both spins. So our equilibrium density operator starts proportional to IZ plus SZ. And the first thing we do is apply a 90-degree pulse selectively to the S spin. Now we know if we apply a 90-degree X pulse, we end up with minus IY magnetization. And now we have evolution, and we'll pretend we're on resonance with the I spin. So if omega, capital omega is 0, then of course there's no evolution during the period of delta due to chemical shift. But there will be evolution due to scalar coupling. So IY or minus IY will have the cosine ij delta, and then minus IY will rotate towards plus Ix as Z. With our rules we have on the board, and no one is on line C. And of course, the SZ operator you use with the scalar coupling, so nothing happens if. And finally, we have the non-selective pulse, which I apply with Y phase. So a Y phase pulse does nothing to IY magnetization. The IX term, a Y pulse, takes X a minus Z. Everybody agree with that? Finger along Y. My thumb along Y, finger on X, will rotate down to the minus Z axis. And then Y pulse takes SZ. So the plus 2IXSZ term becomes minus 2IZSX. And then the SZ term becomes SX. And now I'm going to turn on the receiver and ask what do I expect? So from our rules yesterday, this IY operator will be an in-phase doublet, and its line shape will be dispersive. This term will be antiphase doublet, but its frequency will be omega to the S spin because the transverse operator is SX. This term, the frequency is the I spin frequency. And here we'll have an in-phase doublet. It will be absorptive with the S-spin frequency. So we have an S-spin doublet. It's in phase and a antiphase S-spin doublet. It's also absorptive. Everybody happy with that? Notice that before the 90-degree pulse, we had only transverse I-spin magnetization. If we had turned the receiver on now, after the period delta, we would only see resonance frequencies for the I-spin. After the pulse, we now see a boring part. This is boring. This contains the S magnetization. This is interesting. This S magnetization came from the I-spin. This only exists because of the J coupling. If the J coupling is zero, this term goes to zero. So the appearance on the S-spin of an antiphase doublet tells us that there was a non-zero coupling between I and S. And that's interesting information to have. So this is what we just kind of said. So the first term gives us an in-phase versus doublet at the I-spin frequency. The SX term gives us an in-phase absorptive doublet centered at S with full intensity. And then this term gives us an antiphase absorptive doublet at the S-spin frequency scaled by the sign factor. The problem we have in this experiment is that the signal we're interested in, the antiphase doublet that tells us that there was a non-zero coupling, is overlapped by the in-phase doublet that doesn't tell us anything interesting. So one thing we could try to do first is suppress the signal from the SX operator that came from the SV operator. So how could we do that? So now let's collect a second scan in which the phase of the first pulse is changed from X to minus X. So back up here. I'm now going to do the experiment in which this is a minus X phase pulse. So instead of initially generating minus IY, we'll generate plus IY. And then we just follow that through. And I end up with now this resulting signal. And if I subtract the two, I have this. I inverted the initial Y magnetization. So my ultimate signal, everything that started on the I-spin ended up inverted. And when I subtract, they add together constructively. The SZ magnetization wasn't affected by the first selected pulse. So that signal was unaffected by the phase of the first pulse. So when I subtract the two signals, the SX term subtracts away. So that would be called difference spectroscopy in NMR. I record two signals and subtract them in order to null the signals that I'm uninterested in. And it's the simplest example of phase cycling, in which we'll take spectra with different phases of the pulse sequence, and then add them together in some fashion in order to
get a simplified spectrum that's easier for us to interpret. So difference spectroscopy is a very simple case of phase cycling.
So
here's then what this looks like. The this figure here
is what I would obtain
with
the first
pulse sequence
in which
the phase is plus x. This is what I obtain
with the
first phase is minus x.
And now here
is the subtraction.
This is
the I-spin frequency.
I should have labeled them better.
Here is the signal I was interested in seeing.
The
antiphase absorbed the line shape that came from transfer from the I-spin to the S-spin.
Over
here is the dispersive in-phase signal. It's a little hard to see what's going on. So here the antiphase signal is overlapped with the in-phase signal, and I've subtracted that out over here. So I have purely the signal I'm interested in. Now, to make this more useful, I don't want to have to do selective pulses.
To demonstrate
that I have a scalar coupling between pairs of spins, say in a protein, I would have to do that Gedanken experiment with a selective pulse and keep moving that selective pulse through the frequency band, say in the A mods. And I've been doing this for a very long time. So we have an experiment that tells us the I-spin and the S-spin are coupled together, but it's not broadband.
We want some way of making it
broadband, so we can do it all at once for the protein.
And that's the cozy
experiment. So now I have two
hard pulses,
two non-selective pulses.
But instead of
a fixed delay, I have the delay that I change. Here. So I'm going to start with T1 short, record a spectrum, and then make T1 larger. So now I can just work out what happens. So let me assume that these two phases are both X to begin with. The phases here are indicated by Y1 and Y2. So I'll start with IZ magnetization, apply a non-selective 9-degree pulse, and then allow evolution under the chemical shift scalar coupling for a time period T1. I get the same four terms that we worked out the other day. So you would see these four terms come up over and over again. Here they are. And now I apply a 90-degree X pulse to these. So the first term here, I have minus IY, and X pulse will turn minus IY to minus IZ. And that's shown here. Here, an X pulse does nothing to this first term, but takes Z to minus Y. So I end up down here with minus to I1X, I2Y. Here I have an X operator, nothing happens to it. And here I have a Y, X takes Y plus Z, and takes Z to minus Y. So I end up with minus 2IZ to IY, or I2Y. And now I turn on the receiver and record a spectrum. And what do I see? Oh, by the way, sideway. What's important to me here? Well, this first term right,
right,
is not
detectable.
That's
Z
Z
magnetization.
No
No
signal.
signal.
This
This term
is
is not detectable because it has two transverse
operators.
operators.
So that's the zero
So
quantum.
that's zero quantum and double quantum.
And you
And you decided yesterday that's not observable.
Here, I
have
an
an
in-phase
absorptive doublet.
This is
the magnetization
that
started on the I spin after the first pulse,
and then
and ended up on the I spin.
So
that's going to be a diagonal peak in 2D spectrum. That's not interesting.
It's there.
There.
But
This
peak is
is
now on
spin 2.
It's an
antiphase
signal. It's dispersive because of the
Y operator.
But it's
the frequency of I2,
not
I1.
It
came from
this
term,
where
the X pulse was this to Z and this to Y.
In our language,
this pulse, this 90-degree pulse, was the mixing pulse.
It
transferred some of the I magnetization
from the
I spin to the from I1 spin to the spin I sub 2. That caused coherence transfer. The evolution of the J coupling generated one antiphase state and 90-degree pulse. Flip the antiphase operator to give us antiphase on the partner spin. And that's the interesting peak in the resulting spectrum. Now that notice that peak, the important part is the sign IJT1. We're going to increment T1, but eventually we have to increment it long enough so that this sign term builds up. When T1 is very small, the sign is 0 or near 0. So T1 has to become 1 compared or comparable to 1 over the J coupling, make the sign term appreciable. But while that's happening, transverse relaxation is causing this term to decay away during the T1 period. So the end result of that is the transfer depends on the sign term damped by an exponential decay due to transverse relaxation. And that's going to be generally true, is we're going to have some transfer function. There will be some trig terms, typically sines, and then a damping. And we have to build the sine term up faster than the damping destroys the signal. And that's shown in the figure. If there is no relaxation, and I just get a sine function, and I can set t or increment t as I like to make this a big number. And I get lots of transfer to the other spin. But when R2 becomes comparable to J, you can see I can only transfer about 60% of the magnetization. And as R2 becomes larger and larger, less and less of the magnetization can transfer from the first spin to the second spin because it all decays away too quickly. And this, of course, is a critical part of NMR. We put isotopic labels in order to be able to use big J couplings so that we can transfer the magnetization faster than it decays away. And almost all of modern NMR over the last 3 decades involves trying to find bigger J's and smaller R2s. And we'll eventually see that R2 depends on the rotational correlation time of the protein, how fast it tumbles in solution, times the variance of the local magnetic field fluctuations driving relaxation. And once we put C13 and N15 isotopes, we don't have any bigger J couplings. So that means the only way to improve matters is either to make tau C smaller or make this variance smaller.
And then we can make tau c smaller, for example, by using a thermophilic form of the protein and raising the temperature. Or we can divide the protein into smaller domains, do the experiments domain by domain, and try to stitch the domains together in some way with their temperature. Or we can try to make the magnetic field fluctuation smaller, and one dominant part of fluctuation comes from hydrogen dipole interactions. So we can try to deuterate. And deuterium has a smaller diamagnetic ratio, so it causes smaller dipole fluctuations. Or as we'll see in the case of Rosie, if we have more than one type of fluctuation, if we can arrange to have them offset each other. So this one relaxation effect causes a positive fluctuation in the magnetic field. The other one causes a negative fluctuation. They might cancel each other to some extent. So trosing is making this smaller by finding fluctuations that are anti-correlated with each other. Mechanisms are anti-correlated. So pretty much all of NMR is in here. Development of triple resonance experiments was to use beta J couplings. Trosy and deuteration is to make this term smaller. And then divide and conquer thermophiles to make this term smaller. And get famous, you can think a new way of beating one of these three factors. Basically all there is. There's everything else. There's nothing else they can experiment. You can do to make an experiment with that. So here's the idea. We start with the two pulses close together. Record the signal Fourier transform. Then we move the pulses a little bit apart. Fourier transform. And the signal now is different because it's modified by whatever happened in between pulses. We move the pulses further apart, the signal changes again, so on and so forth. We stack up all of these spectra and do another Fourier transform with respect to this time variable, T1. And we end up with two frequency plane dimensions. The real frequencies. The Fourier transform three induction we measured. And then the frequency dimension wasn't anything directly measured. It just came from whatever happened during this time period increment. You might have thought, why do we do a Fourier transform? You think, I have these spectra. Can't I just fit by, say, least squares? Fit some function as a variation and extract the information. Why don't they just curve thing? Why do we Fourier transform? And it turns out historically it's just way easier to do Fourier transform. Fourier transform is a very robust numerical method. It's very stable, but it has limitations. It turns out we have to sample equal increments. You just can't make these time delays anything you want. We have to increment in a regular fashion and by a time period that's fixed by the nature of the spectrum. So the Fourier transform is very convenient mathematically, but it imposes some limitations on how we can sample data. And you probably all know now that there's lots of NMR efforts now to use sampling schemes to violate the requirements of Fourier transform. These are usually called non-uniform sampling, or NUS. And then one has to abandon Fourier transform and use some other method for analyzing the resulting spectra to get the resulting data to obtain a spectrum. So we'll talk about for a while just the Fourier transform approach. That's how it developed initially. But there's to some extent nothing magical about analyzing this
these data by Fourier transform is just very convenient to store. Interestingly, by the way, the person who thought this up, Jean Genet, never published a paper on it. He thought the idea up of the NMR, and it was in fact this experiment, 2 pulses. He talked about it at a conference, and Richard Ernst students came home and said, wow, you can't believe what we just heard you could potentially do by NMR. Genet was the theoretician, he had to collect the data. He just presented the theory that this would work. So these students came back and told Ernst about it, and they set to work actually showing what worked experimentally. But never heard that. Never published. It's like an abstract in a conference book.
And Ernst won up for the Nobel Prize. Wow.
Now, we of course could care a lot about line shapes, and historically in particularly homework there's a lot of attention paid to what the line shapes were. Once we get the triple resonance experiments, the line shapes are almost always quite simple. So it's not so important anymore. But we'll talk about it here for the cozy. So in the direct dimension, we know what the line shape is. Here we've already worked out our rules. We know that this will be an in-phase absorptive doublet. We know here we're going to have an antiphase dispersive doublet. When we do the second Fourier transform with respect to T1, we're going to be Fourier transforming these trigonometric functions. So the question is, what's the line shape that comes from Fourier transforming sine omega I T1 cosine I J T1 versus sine omega T1 sine pi j. What difference in line shape when we do those Fourier transforms? And it's pretty easy to see how this is going to work. We can use trig identities. First to write this sine times cosine as the sum of chemical shift minus pi j T1 and chemical shift plus pi j T1. And that tells us right away to get a doublet. Because here we have a frequency shifted down by pi j. Here we have a frequency shifted up by pi j. So we're going to end up with the doublet surrounding the shift omega I. This is the two terms are added. They're both positive. So we're going to get an in-phase doublet. So our first rule will be, since we don't want to do this over and over again, is a cosine modulation by the scalar coupling will be an in-phase doublet. We can go on then and write this in terms of complex exponentials using Euler's relation, and we see that we end up with 4 terms, two from this, 2 from that, and in terms of Euler's relation, we have a positive frequency downshifted and negative frequencies, positive frequencies, negative frequencies. You can see that they're multiplied by I. And remember I means a 90-degree phase shift. So these are going to be dispersive line shapes. So we associate a sine modulation by the chemical shift with giving dispersive line shape. So now in the future, I look at this and say, in-phase doublet, dispersive line shape.
This
says that I get when I do the Fourier transform 4 signals.
I get
a doublet centered on the frequency omega I, but I'm also going to get doublets centered on the frequency minus I.
And that is
a bit of a problem.
You're expecting
just to see a doublet frequency centered at the frequency omega I. What is this minus omega I? Why is that? I'll come back to that in a moment. Our other possibility was the sine term. So I do the same thing. I express it in terms of first the sum of two sinusoids. Now you can see I get the difference between the two. So this means I'll have an antiphase doublet. So I associate sine modulation by a scalar coupling with an antiphase doublet. Cosine gave the in-phase doublet, sine gives the antiphase doublet. And once more, I end up with this factor of I. The sine term means that I have a dispersive signal. Now, what about the problem of the frequencies? Notice if we just look at the chemical shift for a moment, the initial magnetization, the chemical shift evolution we had after chemical shift evolution, this minus y term and this plus x term. But after our 90-degree pulse, the y component was up on z, and we only detected the x component. And it's been known for hundreds of years that if you want to tell which direction a rotation is happening, you have to measure both the x and y components of that vector as it rotates. If you just measure one component, you can't tell whether you're going clockwise or counterclockwise. This was known to the ancients who wanted to know which direction a wheel was rotating. If you have an axle and you put a spot on it, and you just look this way, the spot comes around periodically, and you see the spot. But you can't tell just looking at how often the spot appears in front of you, whether the axle is going this way or going that way, because the rotation period is t. The spot appears in front of you. T2, T3, T4, whether it's shot this way or going that way. In order to know whether you're rotating in this direction, you have to look down from the top and tell when I see the spot on this axis, do I next see it on this axis or next see it on the minus y axis? So you always need 2 points of reference to determine the sense of rotation. And you can easily go home and convince yourself of this. By rotating a rolling pin or anything else you have on the axis. So that's been called quadrature detection for a very long time. And if you don't have quadrature detection, then you can't tell whether you have a positive frequency or a negative frequency. Positive going clockwise, or actually counterclockwise by positive or negative frequency. So our Fourier transform here
then when it generates four signals, that reflects the fact we don't know whether our chemical shift was positive omega I or negative omega I. Because we only measured the IX component. We flipped the IY component up to Z. And we didn't see it during detection. So we don't know during the T1 period whether that signal was rotating with a positive omega I or a minus omega I. The X magnetization would have been the same. Now we have two possible solutions. One would be, why would this be confusing? This is confusing because suppose our spectrum has two signals in it, and we put the carrier right here. When we get done with the Fourier transform, we're going to have this peak will have its image over here and make dots. And this peak will have its image over here. Right? This is positive. This one will have an image on the negative side of the carrier because the carrier combines 0 offset. This one that's negative will have an image over here. So our spectrum will have twice as many peaks, and they'll all have reflections around zero around the carrier position. How are we possibly going to tangle this in a complicated NMR spectrum? Now during acquisition, historically, one had a trick by which you can measure both the X and Y components of the signal. So once we measure during acquisition both X and Y, the problem is solved. We can then tell which is positive, and which are negative. So the problem goes away if we measure both X and Y. The other fix, of course, could have been, suppose here's our spectrum. Let's put the frequency here, so that we only have positive frequencies. After the Fourier transform, we'll have positive and negative frequencies. But we only have positive frequencies in our spectrum, so we just throw away everything less than 0. In the past, this was done because if we have the carrier here, then this peak has a large resonance offset from the carrier. And plus, it turns out we have to digitize much more rapidly, twice as fast. So these were serious problems in the past. But now on a modern spectrometer, actually, the way it kind of works is to have the carrier here in the middle during the pulses, and then switch the carrier, at least mathematically, to the edge, because digitizers are fast enough to take care of this problem. So either way, during acquisition, we get around this problem. And the question is how to get around the problem when we are doing this indirect evolution, this T1 period. Is that a question? So what the idea is going to be now is here. So now we're going to do the experiment the second time, but instead of the second pulse being phase X, pulse. Instead of the second pulse being phase X, now the second pulse is going to be phase Y. So what happens now? Now it's the X component that rotates up to the Z-axis, and the Y component remains for detection. So the first experiment will detect only the X magnetization. The second experiment will detect only the Y magnetization. And we store these separately. So now in two experiments, we've measured the X component and the Y component. And now we can tell the two signals apart. We can tell positive away from negative because we have both X and Y. At the cost of having to measure two spectra. And one way or another, that's how essentially all 2D experiments are done. This is called frequency discrimination, quadrature discrimination. There's different ways of doing it. It will be called state TPPI or state PI or states TPPI. N and P type, Rance K. At the end of the day, you're always trying to make sure you have one data set that records evolution essentially of X magnetization, and another data set that records evolution of Y magnetization, or magnetization 90 degrees out of phase relative to the first data set. And then it's a matter of just combine them, and that gets done differently in different experiments. In our particular case, if I just go through the same analysis and then combine the two data sets, I end up with something where I just have a single complex exponential shift. I no longer have the image minus omega. So in this case, I was able to add the two together. There's some experimental details in how one does the combination. We'll come back. That's the general idea. In essence, what's going to happen is I'm going to record one signal in which I have the images have the same absolute sign, and another data set where the image is inverted, or the real peak is inverted. The real peak is inverted. It doesn't matter. So that when I either add or subtract them, in this case I subtracted these two, the image cancels, and I'm left just with the signal that I want. In the spectrometer, the Fourier transform is a linear operator. So because the Fourier transformation is linear, it doesn't matter whether we think of combining time domain data and then Fourier transforming, or Fourier transforming separately the two time domain spectra, and then adding them up after the fact. The way you normally process is to combine time domain data and then do the Fourier transform and end up with one spectrum. But there's no reason why you couldn't take what you think of as real and imaginary parts of your data, Fourier transform them, and then add a spectrum together, which is what I did here. Here's the absorptive and dispersive line shapes. And here's just the simulation then. Back to just simply two spins. Here is the spectrum at four different values of T1. So the spectrum data has transformed in one dimension, and you can see that depending on how long T1 is, the spectrum will be different. if I stack up a whole bunch of these and look up a column, I see something that looks like a free induction decay. But it's not really a free induction decay. They're not actually measured this. This is just this indirect effect. We call these interferograms to distinguish them from the real free induction decay that I actually measure. But I can Fourier transform these, and there's the Fourier transforms. And when this is all put together, this is what the cozy spectrum looks like. Yeah, this is just simulated data. Now, when we looked at the operators and sines and cosines, we would have decided that the diagonal peaks were absorptive, and the cross peaks were dispersive. But that's inconvenient. The dispersive line shape has these horrible tails. So usually after the fact, we then phase shift by 90 degrees. So the diagonal peaks become dispersive and the cross peaks become absorptive. Because then it's easier to look at the cross peaks. But you can immediately see one of the problems with the cozy experiment is if we're looking at cross peaks close to the diagonal, the dispersive tails from the diagonal are going to be interfering with the cross peaks. And hundreds of graduate student and postdoc hours have been devoted over the years to trying to improve this situation. How are we able to look closer to the diagonal and avoid the problems of the dispersive cross peaks? Of course, one hardly runs a cozy experiment anymore. You're unlikely to ever work on a protein small enough that you can run this experiment. So it's kind of a moot point. But even in 1989, became a postdoc and started doing that a lot. The other postdocs in the group were obsessed with how do they get no diagonal cozy? How do they get rid of the diagonals to get close to it? And here's the spectrum of ubiquitin. The main use of the cozy is to look at regions far from the diagonal. Because again, it's close to the diagonal, the dispersive tails making it difficult. So here, this is probably the most important part of the cozy. These are the cross peaks between the amide hydrogens and the alpha hydrogens. And of course, except for proline, we expect one signal here for every amino acid in the protein. You usually don't see the first residue, first amide. The first residue isn't an amide, it's an amino terminal. And that's usually exchanging alpha too fast to see. So we expect here to see the number of residues minus one minus the proline. So this is called the fingerprint. Collect the spectrum. We can count the number of peaks. And if we have way too few, we're worried about the state of the sample. And if we have way too many, we're worried about the state of the sample. For most of you, this is what the N15 HSQC is for. Usually the first thing you do is label your protein with N15, run the HSQC and count on how many peaks you have. And again, we should have one per non-proline residues. So you count them up. Try to avoid counting the trip side chains and acids and blends. You also get worried if you have way too few or way too many. Before N15, this is what one looked at as the very first preliminary characterization. And this has the advantage that it's very far from this region, is far from the diagonal, so the dispersive tail is really not important. Now, here's a blow-up of that region in which spectrum that's
been assigned.
The
The appearance, for example,
this
this peak means
that there's a
non-zero J coupling between amide hydrogen of alanine 46
and
the
H
H
alpha
alpha
of alanine.
of alanine 46.
And that's
very important information to have.
But
What
the
point I really want to make about this is imagine that I made a matrix
in
which
the
rows
where the H
alpha is numbered
from 1 to 76.
from 1 to 76.
Ubiquitin
has 76 residues.
And then the
columns were the amide protons numbered 1 to 76.
And I would put a 0
into this matrix
wherever
the residues
were in
different amino acids,
because
then there's no J coupling
between different
amino acids.
And I could put
either
a 1
or the size of the coupling in
for each of
the residues where there was a coupling.
This
spectrum
is
just a remapping
of
that matrix,
in which
instead of labeling
by red
amino acid number,
the labeling
is by the frequency
of the
amide hydrogen
and the frequency
of the H alpha.
And once
I've assigned the spectrum,
I know
what those frequencies are,
so I can map
this matrix, as it were, back to my original matrix, the matrix that was labeled by amino acid position.
The
matrix labeled by amino acid position
is just
a matrix displaying the chemical shift with scalar coupling Hamiltonian.
That
matrix has zeros in it where there's no scalar coupling, and it has some non-zero number
where there is a scalar
coupling.
So the 2D
spectrum, this 2D cozy,
is just
a representation of the scalar coupling Hamiltonian
for the
amide alpha interaction.
And
all NMR Hamiltonians
are
no more than two spin interactions.
The
scalar coupling is between a pair of spins, it's not between three spins.
The nuclear Overhauser effect is between two spins. In solids, the
direct dipole interaction is between two spins.
There aren't any
Hamiltonians that have three spins in them.
All the
Hamiltonians are some pairwise interactions, or one spin interactions in the chemical shift.
So that means the 2D spectrum, in this case the cozy, or a nosy, or whatever, is a representation of the Hamiltonian. Just transformed from some ordinal labeling to labeling by frequencies. And that means 2D
NMR is the fundamental NMR.
1D
NMR is a projection of the Hamiltonian onto one dimension. 3D NMR is just trying to overcome overlap in the frequency representation.
But there's
no new information.
Can't be any new information
in the 3D spectrum
because we don't have
three spin interactions.
3D experiments,
4D experiments, 5D experiments
are just trying to
resolve overlap.
But the 2D experiment,
is the fundamental representation of the Hamiltonian.
And
that's really a profound statement about NMR and experiment.
So
Ray Freeman, who was one of the pioneers of NMR, was famous
both
for jokes that would get in trouble today,
but
but
also
for aphorisms.
So
So one of his aphorisms was,
a 2D
the 2D experiment is not always the best experiment to run,
but it's
always the best
way to think about it.
way to think about it.
And that's because of this.
And that's because of this mapping of the Hamiltonian frequency space.
Now,
Now,
one thing you'll notice
here, right, is the cross peaks
are all
are
antiphase.
antiphase.
This
Depiction
depiction
where there's multiple lines means the peak is positive,
a
a
single
single
line
line means the peak is negative.
and they're
And they're split by the J line.
But of
course, as the J,
as
as
the
the
protein
gets bigger, the lines get water and water.
and the negative
And the negative and positive
lines
lines
start
start
to
to overlap and cancel each other.
So the
So the cozy eventually stops working
when
when relaxation gets large compared to the size of the J complex. This is the problem we're going to talk about. It is easy to see here
why
that's going to happen because of this antiphase line shape.
There
There
are
are some peaks
that are
that are
missing.
missing. There's a series of peaks that are missing. And you might notice they're all at the same chemical shift.
And they're
And they're
right
right at in
the
the first frequency dimension.
They
They happen to have alpha
hydrogen
hydrogens that are right under the water signal.
And this
In this
particular
experiment,
experiment,
water
suppression
suppression
that
that was done also bleached out those alpha signals.
So
They were saturated, they were suppressed at the same time. Water was suppressed.
So that's
So that's a
a
defect in this experiment.
And then
And then one needs
an
an
experiment
experiment
where
where one can measure those
those
frequencies
without
having to suppress the water in order to get the sign.
And that's
And that's also a problem that continues in NMR, is signals that are under the water or exchange rapidly with protons that are affected by the water.
One
One has to have special handling of water.
You can
You can also see here that glycines
have
have more complicated line shapes,
particularly
particularly glycine 76,
than the
than the
others.
others.
And
And that's of course because glycine has two
alpha
alpha hydrogens. So the coupling is more complicated. The NH is coupled to both of the alphas,
and
and that leads to a more complicated coupling pattern.
And if
If
you
you
go
go
out
out to the side chains,
the
the
coupling
coupling
topology
topology
can
can
become
become complicated,
and the
and the cozy line
line
shapes can become complicated, and it used to be a major business. Inspecting
the
the line shapes in the cozy spectrum
help understand
to help understand what amino acid we're looking at.
not so important.
Not so important these days.
Here is an
example
of the
the fact that we have to increment T1
to a
to
large
enough value that the evolution of the sine term has become large.
That
Sine pi j T1 has to become non-zero for us to have any signal. So
here
is
the
the
spectrum
spectrum
where
where
the
the maximum value of T1 was relatively small.
When we
When we do the Fourier
transform,
transform,
the
the
signals
signals
are
are weak
because
because we haven't let the sine terms evolve enough.
And then
And then here's an intermediate value.
The
The signals are starting to be better, the sine terms are becoming more appreciable.
And
And now here's a large value where we start throwing strong signals.
Of course, if I
kept making T1 max larger and larger, eventually the signals are going to get weaker again.
Because
relaxation eventually kills all the signal.
So there's a
There's a
limit
limit to this.
Again, set by
Again, set by relaxation.
Here's a
Here's a
picture.
picture.
Here's a
Here's a
picture
picture
of the
of the effect of the dispersive tails. Now I'm looking up close near the diagonal,
and you can
and you can see the dispersive tails coming off
and
and interfering with my ability to look at these cross peaks.
What's
What's done
in
in these other panels
is
is change the window function.
Does
Does everybody know what a window function is?
So we
hardly ever just Fourier transform this.
Usually we multiply
the signal by some other function called the window function or optimization function.
And then
Fourier transform. The effect of that is to involve the line shape with the line shape of the window function.
So
we're hoping to improve the appearance of the spectrum by doing this. And in this particular case, a window function has been used that's designed to eliminate the tails, the dispersive tails.
And you can
see as I start to optimize that, the dispersive tails are going away. It's easier to look at peaks up close to the diagonal. There's no free lunch. There's other effects in the spectrum, so one is always playing the game, trying to optimize your ability to detect the spectrum across these you're interested in versus whatever bad effects are coming from the window function.
Yeah,
we can then ask, for example, glycine, what happens? We're going to end up with more complicated sinusoids, and they're all going to look sort of like this. There's going to be a chemical shift term, one sinusoidal term from the J coupling, sine modulated, and then a bunch of cosines. This is called the active coupling. This actually is what gave rise to the transfer from spin 1 to spin 2. And all these other ones are called passive spins. They weren't involved in coherence transfer process. And our rule will be that each of the active coupling is an antiphase line shape, and each of these passive couplings gives an in-phase line shape. And then we can go through, just like we did the other day, and work out what the line shape pattern is by taking combinations of the in-phase and antiphase. So let's just skip ahead of ways, actually. For some reason, that's not the end of this presentation. I should come next. Yes. Now, for the time being, we're doing Fourier transforms. And the Fourier transformation requires that we sample an evenly spaced time intervals. So it doesn't matter whether it's acquisition or the indirect dimension. The signal is sampled even time intervals. So delta t times k, where k goes from 0 out to some maximum value. What's called the Nyquist frequency is 1 over 2 delta t. And there's a theorem that says that our spectrum will then be properly sampled from minus the Nyquist frequency plus the Nyquist frequency. So what you think of as the spectral width goes from minus 1 over 2 delta t to plus 1 over 2 delta t. Or the spectral width is 1 over delta t. So if you have a spectrum that's spread out over a very wide frequency range, to properly sample it, delta t has to be small. Whereas if you have a spectrum that's spread out over a very small frequency range, then delta t can be large. For acquisition, this isn't so important because you're going to be waiting a while during the recycle delay. So it doesn't really matter usually for acquisition. The indirect dimension matters.
And that's
because resolution
in the
in the spectrum
is
is set by
1 over the
1 over the maximum value sample,
not the increment.
not the increment.
The
The
spectral
width
is
is set by
the
the
increment,
increment,
1
1
over
over the increment time.
but
Resolution
is
is set by 1 over
the
the maximum
sample.
sample time.
And that's
And that's one of the main reasons
for
for null sampling
is to
is to try to get away
from
sampling every point
so that
so that you can get out to larger times
by
by not sampling something
shorter.
shorter.
And it's
And it's
easy to see
why
you
you need to get the large times.
So
So suppose I'm sampling
some
some sinusoid.
So
So
here's
here's
a
a
sinusoid.
sinusoid.
And now
And now I want
to
I'm going to change colors.
and now
And now I want to sample another frequency
that's
that's slightly different.
In the
In the beginning, they're very close to each other.
And
And then over time,
they
they
become
become different from each other.
And if
And if I ask it sometime
later,
later,
what's
the phase difference between the two signals?
So the
So the change in phase
is
is equal to
the
the time, say here, times the frequency difference between them. If the frequency difference between them is large,
then
I don't need to sample very long to tell them apart. I get out of phase with respect to each other.
If the
If the frequency
for
for my sampling time is large,
will be
will be an appreciable phase difference.
If I
If I only
only
sample here,
there's
not enough time
to prove
to accrue
difference.
a phase difference,
And I won't be able to.
and I won't be able to tell them apart. Fourier transform data
is
is collected to here.
The two
The two signals are going to be overlapped.
If I
If I collect data out to here,
when I
when I Fourier transform, the signals are going to be resolved. The
ability
ability to resolve frequencies depends on
were
they observed long enough
to
to acquire a phase difference.
This
then
is the
maximum time
that
I need to observe the signals.
So, and this
is something like the difference in
frequencies.
frequencies.
So
roughly speaking,
the
difference in frequencies that I can resolve
will be
something
something
like 1 over the maximum time
that
I observe.
So if I have a very small increment
to cover a big spectral width,
I mean, I
have to acquire many points
in order
to also have good resolution.
And that's
really a key trade-off
with the
Fourier method.
What
happens
if we
sample with too large an increment?
Now
I have two signals,
but my
sampling points are the black dots. I have two different frequencies.
You can see
that they're different, solid line and dashed line.
But at
the points I sample,
the two
signals are crossing each other.
So when
I Fourier transform, I collect
data, I can't tell
those two signals apart. I can't tell that I had two different frequencies.
Because I
happen to have sampled them
when
the two frequencies have the same amplitude.
This is called
aliasing
in NMR,
or folding.
And that's shown
then here.
Here I have
some
wider
spectral width.
If I narrow the
spectral width down,
this
peak appears artificially in the spectrum. This peak appears artificially in the spectrum somewhere else.
Where they end up will
depend on how I did my quadrature. Most of the time, the way you're currently collecting data, the spectrum behaves as if the two edges are connected in a circle.
And something peak outside to the left
reappears on the right.
And something that's
off on the right reappears on the left.
So you can think
of the spectrum that you have,
that your spectrum
width is a barrel
of some
circumference,
and your
spectrum is just wrapped around that barrel.
And if your spectrum is
wider than your spectral width,
peaks will wrap
around on top of each other.
And that's
aliasing. One can collect the data in such a way that instead of being a barrel,
the edges of the spectral
mirrors
and reflects the peaks
back in.
But that's, those modes
of data composition
aren't used so often
these days.
And that's probably enough. All
I want to say about sampling right now is
that we
have this requirement that the increment be small enough to cover the spectral width we're interested in, and then the total time be long enough for the resolution to resolve the signals. This, by the way, should seem like a major issue.
What's the spectral
width of random noise?
If you
had white noise
and
Fourier transform,
what frequencies
would you expect to see?
Could be
an almost infinite range of frequencies, right? Random noise jittering around could have all sorts of frequencies in it.
The noise
in an NMR experiment
is
really just limited by the bandwidth of the electronic devices. An electronic device that's measuring some signal never has infinite bandwidth and can't be built.
So there's some bandwidth
limitation in the amplifiers, the preamplifier.
But that
bandwidth is probably way larger than your spectral width. And that means all the noise
outside your spectral
width is going to alias and fold back into your spectrum.
That seems
like a really bad idea, doesn't it? The signal to noise is going to be rated
by all this noise
outside the spectrum width folding in.
To get around that,
spectrometers all have filters
to filter
out the noise
outside of the bandwidth,
outside of the spectral width that you set. In the old days, these were physical filters built from electronic components, and they would have the property that they would distort this region of the spectrum near the edges of the filter width. So the filters had to be wider than we actually wanted them to be to avoid these artifacts. These days now, one has digital filters that are very powerful. So the physical filters tend to be set fairly wide. You record the data, and then the digital filter is applied to that data to give nice clean cutoffs that avoid folding in the extra noise left over by the physical filters. And if you look on Brooker's spectrometer, there are settings that you hardly do anything with these days. They're set automatically about what the physical filter width is and what kind of digital filter is being used to cut down the noise that's let in by the physical filter.
All right, so let's
stretch for a moment and then do some problems.